Okay, in this lecture, we are going to start electromagnetic induction. Is a very important topic, electromagnetic induction. So, the idea behind the topic is credited to actually Michael Faraday, who investigated this question: can we produce magnetic field? Can we produce current from magnetic field? Can we produce current from magnetic field? That was the idea that was explored by Michael Faraday, one of the all-time greats, and this topic is entirely due to his credit. Can we produce current from magnetic field? So the laws in electromagnetism are all experimental. First thing I want to tell you is a law cannot be proved. You can verify it experimentally. Law can be verified experimentally, but it cannot be proved. It is the working of nature. For example, a positive charge attracts negative charge. If you ask me why, it's very difficult to answer. I know it attracts and I can give a law which will tell you the force of attraction. But why does this positive charge attract negative charge? That's something that's very difficult to tell. So, first let us look at some rudimentary experiment. Probably Michael Faraday would have gone through such experiments and then would have given his law. So, one of the experiments is I have a magnet with south pole and north pole, and I have a plain wire. It's in the form of a loop. Of course, I have connected a galvanometer to it. It's just a plain wire, a circular wire with galvanometer connected, and I am experimenting. Can this magnet, which is producing a magnetic field, can it produce current in this wire, in this circular loop? If there is a current, the galvanometer will show some deflection. So probably Faraday would also have done same experiment. First he would have kept a magnet here and this wire, and then he would have waited for 3-4 hours thinking that, hey, magnetic field, produce current. Hey, magnetic field, produce current. But the galvanometer doesn't show any deflection. So then Faraday thought, okay, it doesn't work this way. Then as he started removing the magnet, suddenly the galvanometer is showing some deflection. Very interesting. When the magnet moves away, the galvanometer shows deflection. Or when the magnet moves towards, the galvanometer shows deflection. Very interesting. As the magnet moves away, the galvanometer shows deflection. As the magnet moves towards the loop, the galvanometer shows deflection. In fact, the faster the magnet moves, the more the deflection. It may be towards or it may be away, but the faster the magnet moves, the more the deflection. Not only that, if you change the area of the loop, then also there is some deflection. You try to compress the loop, okay, or you try to expand the loop, then there is some deflection in the galvanometer. Or even if you rotate the loop about certain axis, about its diameter, for example, you rotate the loop about its diametrical axis like that, okay, then also there is some deflection in the galvanometer. So please note, this plane of the loop that I have drawn in this figure is perpendicular to this direction, okay. So if I show you a different view, if you say this is the loop, you are bringing the magnet towards the screen, towards this loop basically. So the plane of the loop is perpendicular to the direction in which you are bringing the magnet. So keep that in mind. Anyway, so if you move the magnet towards the loop, there is a deflection in galvanometer. You move the magnet away from the loop, there is a deflection in galvanometer. You expand the area of the loop or compress the loop to reduce the area, there is deflection in galvanometer. Or you rotate the loop about this any diametrical axis, there is a deflection in galvanometer. Now, not only moving the magnet towards the loop, you can even move the loop towards the magnet and you will see a deflection. Even if you take the loop away from the magnet, you will see a deflection. So if I jot down all these points, it looks like this. Okay, as magnet moves towards loop, current is produced. Galvanometer deflects because current is produced. So current is produced. Or you can say as magnet moves away, current is produced. The faster the motion of magnet, more current. Not only that, if area of loop changes, then current is produced. If loop rotates about its diameter, then current is produced. Current is produced. Okay. Even if loop moves, that means indirectly I am saying if there is relative motion between loop and magnet, if there is relative motion between loop and magnet, then current is induced. See, all these points which probably would have been observed by Faraday would help him to relate the current in the loop, or in the first place why there is a current, because there must be some electromotive force in the loop. So all these points would have led Faraday to conclude that the EMF in the loop is a function of the velocity of the magnet, the velocity of the loop, the area of the loop, the angular speed with which the loop is rotating about its diametrical axis. So if I was Faraday, or if some of you were Faraday, probably we would have been forced to think that the EMF is function of so many variables: velocity of the magnet, velocity of the loop, area of the loop, and angular speed of the loop. Probably you could reduce one variable by taking relative velocity of the magnet and the loop. Instead of taking Vm and Vl, you can take the velocity of approach or separation or something like that. So we would have got a very complicated formula relating the EMF in this circuit, the electromotive force which is responsible for current, in terms of all these quantities. But the genius of Faraday, he is such a great genius that he explains all these points, all the points that I have written, with just only one thing. See, as the magnet moves towards the loop, the lines of magnetic field entering the loop are changing. Okay, number of lines of magnetic field entering the loop is changing, and you can call this quantity visualistically as flux of magnetic field. So as the magnet is brought closer to loop, lines passing through the loop are changing, so flux of magnetic field is changing. Similarly, as magnet moves away, again lines of magnetic field passing through loop are changing, flux is changing. The faster you move the magnet, the faster these lines are changing and more current. Similarly, if area of loop changes, you are accommodating more magnetic field lines passing through the loop, so again flux is changing. If loop rotates, again when the loop area is perpendicular to the direction of motion of magnet, more lines enter. When loop area is parallel to the direction in which magnet is moving, no lines enter the loop, no line. So again this is explained by understanding the number of lines that are passing through the loop. Okay, if the magnet and the loop move with same velocity means same speed and same direction, then there is no current induced, because number of lines of magnet entering or exiting the loop is not changing in that case if both are moving with same velocity. So all these points are explainable with just one thing, and that is current is produced if number of lines of magnetic field passing through loop changes. This quantity is called flux of magnetic field. Number of lines is called flux of magnetic field. Passing through the loop is called flux of magnetic field through the loop. Flux is always calculated through an area. So number of lines of magnetic field passing through certain area is called flux. Of course, the number of lines depends on the person who is drawing. I can draw 100 lines and you may draw only 50 lines. So that's not a good way of defining flux. Even though visualistically you can visualize more lines, more flux, and less lines, less flux. But still, I could draw more number of lines and you could draw less number of lines, and we can have an argument saying I would say flux is 100 and you would say flux is 50. So we need a more precise mathematical definition for flux. But the main idea is only when flux of magnetic field through a loop changes, there will be EMF. And so Faraday went on and gave his famous law, which I am about to write here now. Faraday's law, extraordinary law by Faraday. So Faraday says if the flux of magnetic field through a loop through certain area is changing, then derivative of flux simply gives you the EMF established in the loop. What is meant by EMF? I will talk about it in great detail later, but you can think that as flux changes, there is some invisible battery or a cell being established in the loop driving current, an invisible battery or invisible cell. For now you think like that, but I would go on later in great detail to explain this concept of EMF or electromotive force in a very interesting way. So this is what I call as Faraday's law. Faraday's law. So if you want to establish EMF in a loop and produce current, you have to change the magnetic flux through the loop. That also means something very deep. See, if I just have a magnet here and if I just have some loop here, okay, if I don't move the magnet, no current is being produced. That means unless you don't do work, magnetic field cannot produce current. You can't say magnet please produce current without doing any work. That's not correct really. It violates the law of conservation of energy. So if you start moving the magnet, if you are giving kinetic energy to the magnet, you will feel some resistance as you try to move. You will feel some opposition. And in spite of that, if you are able to move the magnet, a current will be produced in the loop. So essentially the work you are doing is being converted into current, and or I would say the heat energy that will be liberated in the resistance of the wire. So the work that you are doing is being converted to the electrical energy in the wire. So the important thing is you have to do work to produce current or to generate energy or to run your equipment. That's the basic idea. Magnetic field doesn't do any work. It is just only a conversion factor. Even for example, if you take one magnet and push another magnet, you might be tempted to say that magnetic field is doing work, but no, if you go into the internal structures and go much deeper into it, magnetic field doesn't do any work. There may be some induced electric field which is doing work, that's a different issue. So we will see some of these concepts down the line, but this is what I call as Faraday's law. Derivative of flux gives you EMF. Such a simple law. Such a simple law. Otherwise, if we were doing this experiment and trying to write the law, we would say the EMF would depend on velocity of the magnet, velocity of the loop, angular velocity of the loop, area of the loop, and so many other factors. Probably we would have gone into that route and made it very, very complicated and cumbersome. But Faraday's beauty, his visualization, enabled him to write such a simple law. So this is what I call as Faraday's law, or this is what I call as electromagnetic induction. Technically speaking, after discussing this, the topic is over, but then it is not over. It's not that easy. For example, if I write net force is mass into acceleration, I would have understood Newton's law, but then there are so many other things. There are constraints, pulleys, wedges, and extension of Newton's law into work energy concepts, and the conservation of momentum. Impulse momentum theorem comes from Newton's second law only. So there are so many things. Newton's second law is just a simple statement, but it has got great depth. Similarly, the Faraday's law looks very simple, and I can say the topic is over, but then there are so many complications down the line, which we are going to see now in a systematic way. But before that, I want to discuss something about how to calculate flux. Suppose if I have a plate like this of area A, And suppose there is a uniform magnetic field. Uniform means it does not change its value with this location. Generally, there are two terms that we use with magnetic field. One is uniform, one is steady. A uniform magnetic field has got same value at all locations, but it may change with time. For example, today in my room there may be magnetic field of 3 Tesla everywhere. Tomorrow it may become 4 Tesla. It is changing with time. That is uniform but unsteady. Unsteady. Whereas steady means it doesn't change with time, but it may change with location. For example, in my room magnetic field is 3 Tesla. In your room magnetic field is 4 Tesla. Even after a million years the situation is same. So it's not changing with time, but it changes with location. In my room it has one value and in your room it has a different value. So for now we are going to consider a magnetic field which is uniform and steady for now. Down the line I would take magnetic fields which are uniform and unsteady, or sometimes non-uniform and steady also we will look into. Okay, even non-uniform and unsteady also is possible. So right now my magnetic field that I am going to take is uniform, does not change with spatial location, and it is steady, does not change with time. I am going to take such a magnetic field. So let us say such a magnetic field is perpendicular to this plate and the value of magnetic field is B. Then I can define flux through this loop or through this area. Flux is always calculated through an area as BA. You can say BA is the flux. This definition is very simplistic. It may fail in certain scenarios. So better definition than this is, for example, if you have the same plate but magnetic field is not perpendicular to area, rather it is making some angle with normal to the area. Suppose it is making some angle theta. Then I would like to split this magnetic field into two parts. B cos theta, which is perpendicular to area, B sin theta, which is parallel to area. When you are calculating flux, you should take only the perpendicular component. So B cos theta into A. That's a better definition of flux, which you can write as B dot A. And here we are taking area vector. Area vector is perpendicular to area. Of course, there are two possibilities. If you have certain area, you may take a vector perpendicular this way also, that way also. There is some ambiguousness there, but still area vector is perpendicular to area. So if magnetic field is already perpendicular to area in the first case, that means it is parallel to area vector. That means angle between magnetic field and area vector is 0. So BA cos 0 will boil down to the original definition BA. In this case, area vector is in this direction perpendicular to area, that is area vector, whereas magnetic field is like this. The angle between them is theta. So if you do this dot product, you get BA cos theta. So better than just BA is this definition B dot A. So flux is given by B dot A. But even this definition is not general. It might fail. For example, you can have certain area, certain plate, where here magnetic field may have one particular value, here it may have a different 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 value, and so on. So in that case, throughout the area there is not one particular value of magnetic field. Then you have to chop this area into many small little areas. So I will take a small area dA. In fact, I will take area vector. I will find magnetic field at that location and do dot product. That gives me flux through that small area. Such fluxes you have to add. So that gives me the total flux. So that is the most general definition of calculating the flux. This is the most general definition. It will never fail. Most general definition to calculate flux. So if somebody asks you how do you define magnetic flux, you should go into this definition, integral B dot dA. Of course, if B is having a constant value in both magnitude and direction throughout the area, then this definition will boil down to the fact that you can take B out of the integral and you can add all little area vectors. That will give me total area. It will come back to this definition only. And if magnetic field is also perpendicular to area, it will come back to this definition only. So this definition encompasses everything, encompasses or includes every other definition of calculating flux. So I would say flux of magnetic field is given by integral B dot dA. So that is the first thing you should understand, how to calculate flux. Once you calculate flux, if it is changing, then EMF is induced in that loop. in that loop, or EMF is induced in that location. Okay, EMF is induced in that location. So flux must change for there to be an EMF. So this is one thing. I will just take a very small example on the calculation of flux. For example, I have, this is my y-axis, let us say, this is my x-axis. I have a loop whose length is L. Okay. Let us say there is a magnetic field in this region which is given by B naught x k. So you see this is a very strange magnetic field. The direction of magnetic field is k, that means along z-axis. Z-axis is outward. Okay, in the right hand coordinate system, if you do cross product of x and y, that will give the direction of z. Okay, now this magnetic field is pointing along k, along z direction, but its value depends on x coordinate. Please note that. So it is not a uniform magnetic field, it is changing with location. And I want to find flux through this area, flux of magnetic field through this area. One thing is sure, magnetic field is perpendicular to the area. That we are very lucky. Magnetic field is pointing in z direction, whereas area is in the xy plane. So magnetic field is perpendicular to area, no doubt about that. But the problem is it is changing with location. So what I am going to do, at a distance x, I am going to consider a strip, thin strip like that, whose thickness is dx. Okay, whose thickness is dx. That means whatever is the magnetic field at location x, approximately, I shouldn't say even approximately, that is the value of magnetic field at x plus dx also, because my dx is tending to 0. And what is the magnetic field at x? It is B naught xk. So B naught x is magnetic field, that's already perpendicular to this area which I have shown here. So magnetic field multiplied by this area. What is this area? L dx. Because length of this strip is L, thickness is dx, or width is dx, so L dx is the area. So magnetic field at that location into area, that gives me the little flux in that area. If you want total flux, you have to integrate with x going from 0 to L. So it will give me B naught L into x square by 2. On putting limits, it will give L square by 2. So B naught L cube by 3. Weber. Flux is measured in Weber. That's the standard unit of measuring flux. Please note, be very careful. Magnetic field is measured in Tesla. Here B naught has units Tesla per meter. Please note, because Tesla per meter multiplied by this unit meter gives you Tesla. So B naught is not magnetic field. B naught is Tesla per meter. X is measured in meters. B is measured in Tesla. Okay. So flux is B naught L cube by 3, in this case Weber. So two things, magnetic field is measured in Tesla, standard unit. Magnetic field is measured in Tesla, and flux, magnetic flux, which is calculated through an area, is measured in Weber. Weber. Please note, flux is magnetic field into area. So Weber is Tesla into meter square. So you can also say Tesla is Weber per meter square. Please note, these are all very important ideas. I mean, conversion units, very important ideas. Okay, so this is the example I was intending to take. Now with this background, let us go into Faraday's law again, and let us look at Lenz's law. Lenz was another scientist who came and put a minus sign in front of Faraday's law, and a name is attached to him. But it's not so simple. If you and me were to put a minus sign and say it is Kalyan's law or somebody's law, that won't work. That's crime actually. Lenz actually gave a lot of thought to Faraday's law, and he came up with a brilliant idea and put a minus sign, and we will see the significance of that soon. Okay, so I'm just going to erase all this. So Lenz's law, so E is minus d phi by dt. Previously we wrote E as d phi by dt, but now Lenz came and he has put a minus sign. And the significance of minus sign, this negative sign is due to Lenz, This negative sign is due to lens. Significance of this negative sign is as follows. The EMF and the resulting current, if the circuit is complete, the resulting current, if circuit is complete, would be such that it would oppose the original change. That's very strange. This statement is very confusing, but it is very, very deep. So I would try to explain the idea. The minus sign, significance of minus sign is, you can even get away with minus sign if you remember this statement. The EMF and the resulting current, okay, current will be there only if the circuit is complete. It's a closed circuit. Okay, so the EMF and the resulting current would be such that it would oppose the original change. What do you mean by oppose the original change? So let's look at that. Suppose I have a loop, okay, and there is a magnet with north and south, and suppose I release the magnet, this north pole is coming closer to this loop. So north pole is coming closer. That means the current that will be produced in flux is changing through this loop, so current will be produced. The current that will be produced in this loop should create north and south poles in such a way that it should oppose the original change. What is the original change? Magnet coming down is the change. We want to oppose that. Means we should not allow the magnet to come close. And that is possible if the top surface of the loop becomes a north pole, so that north is actually repelling this north, opposing the change. When will top surface become north pole? See, there is a rule which I want you to remember. If current is like this in a loop, then that face will act as north pole, and if current is like this in a loop, that face will act as south pole. You see, if you write S and put the direction of arrow, it coincides with this. Similarly, if you write N and put the direction of arrow, it coincides with that. But please be careful. So anti-clockwise, this face is north, but somebody who is seeing from behind this white screen, for them that will be clockwise, that will be south pole. So the moment there is a current carrying wire, you have both the poles, north and south pole. You can't avoid. You can't have a monopole in nature. That's against the law of nature. You always have a dipole in magnetism. In electrostatics, you can have mono charge. Positive charge alone is possible. For example, from hydrogen, remove electron, you remain with a positive charge. Only negative charge is also possible. So mono charge is possible, but monopole, just having north pole is impossible. North comes with south. They both are like husband and wife. North comes with south. Okay. So in this case, the top face must be north, means as seen from top, the current must be anti-clockwise like this, as I have shown here. Okay. In fact, I can even draw like this. North, that would point out to this direction of current. So when the magnet is left, it is coming closer to the loop. We should oppose this. North pole coming closer, the loop says, please don't come close. Please don't come close. So it will also become north, trying to repel that. Top face is north. Of course, bottom face will be south, no doubt. Bottom face is south. So on the whole, what is happening? If you leave the magnet, there is a force mg due to Earth's gravitational pull, and there is repulsive force because of the induced current and this current carrying wire becoming a magnet. So net force is less than mg now. So acceleration of this magnet is less than g. Okay, because there is this upward repulsive force also. Net force is mg minus f, net force. So acceleration will be mg minus f by m. Acceleration will be mg minus f by m, that is g minus f by m, that is definitely less than g. So when you release a magnet above a loop, the magnet's acceleration will be less than g. Now let us see what happens when the magnet passes through the loop and comes down like this. Now here you have south pole and here you have north pole. Now south pole is going away from the bottom face. We must oppose the change as per Lenz's law. So south pole going away, The loop says, no, don't go away, be near to me. Okay, you always oppose, reverse gear. It's a common theme in Indian households that there is a joke that wife doesn't agree to husband. So suppose you want to take your wife to movie and you know that forward gear doesn't work. So say to your wife, today I don't want to go to movie. And she says, no, we will go. So always you are using reverse gear. That's an interesting joke. Anyway, here South Pole is going away from this loop. So the current in the loop will be such that bottom face will be north, trying to attract south, saying don't go. Bottom face is north, so top face must be south pole. So current will be like this, clockwise. So while the magnet was coming down, as long as it was above the loop, current was anti-clockwise. The moment it goes below the loop, current is clockwise. It reversed. It reversed. So Lenz's law is always oppose the change. Current should be such that it should oppose the original change. That is the interesting idea. So you can as well remove the minus sign, but you should remember the statement. The current that is induced or the EMF that is produced is such that it will produce a current. The EMF will produce a current such that it will oppose the original change. That is about the Lenz's law. I will show you another example. It's better to go to another example. Suppose I have just a plane loop, and let us say there is a magnetic field going into this plane and it is increasing. It is increasing. That means flux through this loop is changing. So immediately a current will be produced in this wire such that it will try to reduce the flux. Right now flux is increasing. So as per Lenz's law, we must oppose the flux. How can you oppose the flux? The magnetic field is increasing inward. So the current that will be produced will produce a magnetic field outward. And that is possible if there is a anti-clockwise current, because an anti-clockwise current will produce an outward magnetic field here. Okay, you curl your fingers along the direction of current, thumb will point outward. So this current carrying wire is producing outward magnetic field, which is trying to oppose the inwardly increasing magnetic field. The same way, if the inward magnetic field is decreasing, then we have to reinforce it. Then current will be clockwise, trying to reinforce the inward decreasing magnetic field. So here magnetic field was increasing, current is anti-clockwise. Here magnetic field is decreasing, current is clockwise. So this is all as per Lenz's law. So I hope you understood the idea behind the Faraday and the Lenz's law. Now let's go into problems, because by doing problems only here we can understand really all the ideas very thoroughly. So the very first problem that I am going to take is a very instructive one, very important one. It puts a lot of emphasis on all the concepts. So from here onwards I will be doing a lot of problems, and in between I will also be introducing some of these concepts. So the very first problem which I have is, there is a wire with some resistance R, okay, which is like this. The wire looks like that, and it is put on a smooth floor. It is fixed to a smooth floor. Let's say it is fixed to smooth floor, so it is on a horizontal plane, and there is a slider, something which can slide on these two wires. These two wires are sometimes called rails because they look like a railway track, and this slider can slide on these rails. So these are called rails. And let us say the length of the slider is L. Length of the slider is L, and there is a magnetic field which is uniform going into the board. So this is a uniform plus steady magnetic field going into the board. Uniform plus steady magnetic field. The slider has got length L. I would show the slider in a much more interesting way than this. Let me show it. I shall use a different color maybe. I'll just show it like that. Okay, just a small thing like that. That's my slider. Now somebody is pulling the slider, somebody is applying force and pulling the slider with a constant velocity. So an external agent is pulling the slider with constant velocity. This statement is very ambiguous. I'll explain, but please note these rails are also smooth. There is no friction between slider and the rails. There is no friction between slider and rails. Now you see external agent is applying force on the slider, but on the other hand, I am saying it is moving with constant velocity. A force must accelerate the slider and increase the velocity. But why the hell am I saying that it is moving with constant velocity? So that means there must be some other force which is opposing the force I am applying. So net force is zero and velocity can remain constant in that case. So we have to explore that possibility now. Anyway, the question pertaining to this situation is as follows. There are many bits to this question. First A, the slider is moving with a constant velocity v, that is given. Okay, the velocity is also given. So bit A is find the EMF induced in circuit. So let's talk about this in a minute, but that is the first bit. Second, find current in the circuit. Find current in the circuit. Third bit is find the force on the slider due to magnetic field. That C bit will clarify the fact that why the slider's velocity is constant in spite of me applying a force. Okay, that will clarify. Part D is find power liberated in resistor. Find power liberated in resistor. And part E is find power exerted by external person. Find power exerted by external person. And I also want to discuss the F bit, which is very interesting. Where is the EMF induced in the circuit? If it is induced, where is the EMF induced in circuit? Okay, so we have to discuss all these things one by one, step by step. So let's look at this. So this is a C-shaped wire put on a floor. Resistance is R. There is a uniform and steady magnetic field going into the plane of this, into the board, let us say. Slider is being pulled with a constant velocity. Now, first of all, let me take the position of slider from left end as X. Let's take it as X. This position is changing because slider is moving. So rate of change of position dx by dt is going to be V. This we will use somewhere. I'll call it star. Okay. Now let's go to the physics behind the problem. What is happening here? As I move the slider, this area which I am showing here with the marker, this area is increasing and there is a magnetic field going into the plane. So on increasing area, you are allowing more lines to pass through this area. So flux is changing. If flux changes as per Faraday, there will be EMF. So what we are going to do, we are going to write flux at any instant and differentiate it to get EMF. Okay, so right now at this instant, X is the distance of this slider from left end. L is the length of the slider. So this area which I am showing here is Lx, and magnetic field is anyway perpendicular to area. So my flux is going to be, which I am going to write in the next page, my flux is going to be, magnetic field is already perpendicular to area into Lx, and it is changing. This is changing because X is changing. This is changing because X is changing. So EMF will be d phi by dt, derivative of this. So d by dt, that is Faraday's law, d by dt of BLX. B is uniform and steady, constant in magnitude and direction. Length of the slider is fixed. dx by dt is V. We saw that here in star. Previous page. Here we have dx by dt is V. So the EMF induced in this circuit is BLV. Believe me, this formula will help you later solve almost 60% of questions in this topic, in my opinion. So EMF is BLV. We'll later refine this formula. This is cornerstone of this topic. Cornerstone, or very important, of this topic. Very, very important idea here. EMF is BLV. Okay. Please note, flux EMF is d phi by dt is a general rule. Okay, EMF is d phi by dt works no matter how flux changes. Flux may change because magnetic field is changing. Flux may change because there is motion. Whatever be the case, this law will always hold. Okay, this is the most general law. So you can change flux by changing magnetic field. Here in this case it is not changing, of course, or by changing area, which is changing in this case, or both. Even if both changes also, still this is valid. So E equal to d phi by dt holds irrespective of how flux changes. This point may look very silly right now. Later we will look into motional EMF and induced EMF, and later a combination of them, and still this law holds. Okay, so that is my idea in putting this point upfront before we go to those topics. Anyway, let's go to second question. Find the current in the circuit. Once I know EMF in the circuit is BLV, this EMF is driving a current and resistance of the circuit is R. So current will be BLV by R. Okay, suppose if you had a cell somewhere in this circuit of value BLV, current would have been BLV by R. No? So this EMF is somewhere hidden, I don't know where. We will explore that point. EMF is induced in the circuit because flux is changing. But where is this EMF? Is it here, or is it there, or is it there? Where it is, or is it everywhere? So we have to explore that very carefully. So we will look into that soon. But the current in the circuit is EMF by resistance. Now this is the current. How is this current flowing? Now we have to use Lenz's law. Look very carefully. Area is increasing, magnetic field is constant in magnitude and direction, area is increasing, so flux is increasing. So induced EMF or current must be such that we must oppose the change, means we must try to decrease the flux. It is increasing, we don't like it, we want to decrease it. That's what Lenz's law says. How to decrease the flux? Maybe try to reduce the area, that is not in your hand. Maybe oppose the magnetic field. Magnetic field is in, let's create an outward magnetic field. That's possible only with this current in this direction. So current is flowing in anti-clockwise direction. It is opposing the magnetic, it's creating a magnetic field which is opposing the existing magnetic field. You see, if you have a current carrying wire like this, in this region it creates a magnetic field which is outward. That comes from Biot-Savart's law, which is from another lecture. Okay, but in a way you can use your right hand rule. Put your fingers along the anti-clockwise direction, right hand fingers, thumb is pointing outward, so that is the direction of magnetic field due to this current. So current is anti-clockwise. That means current in the slider is going from bottom to top like this, bottom to top, and going like that and like that and like that. Okay, now immediately because of that we have this C part. Find the force on slider due to B. The moment you have a current carrying wire in magnetic field, it experiences force, which is from the other topic, other part of magnetism. And the force on a current carrying wire in magnetic field is given by F equal to IL cross B. This is the law that describes force on a straight current carrying wire in magnetic field, straight current carrying wire. So in this case, IL, what is L vector? L vector is length vector in the direction of current. So this is L vector. L vector and B vector is into the plane. Okay. So imagine a vector, this is a red vector, and into plane another vector. For example, this is L vector. B vector is into the plane. I am showing it like that. Imagine it in 3D. This is L vector, this is B vector. We are doing cross product. How do you do cross product? First form a plane containing these vectors. You should join them by tails. Form a plane containing these vectors. Put a screw perpendicular to plane, like this you put a screw at the tails only. Rotate from L to B by smaller angle. So if you rotate the screw clockwise, it goes inward. So that is the direction of force, L cross B. So here force on this wire is given by IL cross B, that is I L B sine 90. Why sine 90? Because angle between L and B is 90. Length vector is this and B is into the plane. Both are at perpendicular. Any line on the plane and any line perpendicular to this whole plane, they both have angle 90. So that is the magnitude. So ILB sine 90, that is I, we already found out. I is BLV by R. Just previous bit we found out. So I will put that BLV by R into L into B, that is B square L square V by R. And what about the direction of the force? This is the magnitude of the force. What about the direction of the force? L cross B, we saw it is pointing to the left. Okay, you should understand cross product to get to directions. I discourage people from using right hand left hand rules and so on. Just do cross product, it will be very interesting. So the force is to the left, so there is this force acting on the slider to the left. So you see, slider which I have shown previously with orange color, I am pulling it to the right with certain force, but there is a force because of current flow in this slider to the left of value b square L square V by R. And I must also be pulling with same force because it is moving with constant velocity. So this is the force applied by me. This is the force applied by the magnetic field on current carrying wire, which comes from some other topic in magnetism, which is in another lecture. So I am applying the same force, and there is the magnetic field is countering with this force. So ultimately net force is 0, wire continues to move with that constant velocity. Initially, who provided this constant velocity? That's not my subject of discussion. I don't know who. Maybe this person only initially exerted more force and made it move, and later net force was 0 and it is moving with constant velocity. So we have done bit A. EMF is BLV, current, that is BLV by R, force that we just now calculated as b square L square V by R. So I am going to write it here, b square L square V by R, that is the force. Power liberated in resistor, simply that is I square R. We already got I, that is b square L square V square by R square, multiply by R, so it will be b square L square V square by R. That will be power liberated in the resistor. Power exerted by external person is F dot V, the force he is applying, dot product with velocity. This is the formula for calculating power in mechanics. This is the formula for calculating power in current electricity. You see, I am going in different routes. But the force applied by external person is also same, b square L square V by R. B square L square V by R, and force and velocity are in same direction, so multiply by V. So that will also be b square L square V square by R, same as this power. So here I must tell you, whatever power person is applying, that is coming as heat. Magnetic field is not doing any work, please understand this, it never does work. Whatever work you are doing, it is being converted to heat, electrical energy. So the power liberated in the resistor is same as power exerted by you. That means power liberated in certain time in the resistor is work done by you in that time. Okay, so power liberated by external person, power liberated in resistor and power exerted by external person are same. Last bit, where is the EMF induced in the circuit? Somewhere, I don't know where. That means indirectly I'm asking, where is the battery? If there is a battery of value BLV, where is it? But we will see soon. It's going to be in the moving portion of the circuit, and here the slider is moving, so the slider itself behaves like a battery with this polarity. Okay, now it is, you can replace the slider with a battery like that of value BLV. It's possible, and we will see the theory behind that soon in one of our upcoming lectures. So that is the idea of this Faraday and Lenz law. We will see many more questions in our next lecture. Thank you.